correctly, we first extract the text from the document and then compress that text much more efficiently. This is the overall architecture of our system. The user uploads an image through our next.js frontend, which sends it to our fast API backend. Instead of the backend, we perform OCR, and stage 2 compresses the extracted text using adaptive Huffman encoding before returning all the results back to the frontend. For OCR, we trained a custom 4-layer CNN on MNIST digits and generated character crops. We also trained it with Gaussian and salt and pepper noise augmentation, so it performs better on noisy scans. Here, I'm uploading an image into our posted product. So once the image is submitted, the OCR service processes it and returns the generated text. Now, I'll show you how that text is actually generated internally. So first, we start with a single character image. The image goes through pre-processing, blob detection, crop normalization, and then gets classified by the CNN. Now, for a full clean image, we first separated it into horizontal projection, then connected components are used to detect character blobs. Those blobs are converted into crops, resized into 28 by 28, and then sent into the CNN. Finally, the gap analysis is used to reconstruct the spaces between the words. Now, this is where our main contribution comes in, handling noisy images. For the noisy version, pre-processing becomes much more important because image may contain Gaussian or salt paper noise. Even after thresholding, extra blobs can appear, so we remove tiny connected components and background regions. Another challenge is that noisy characters often merge together into one white blob, so for those cases, we use vertical projection. So now moving on to the stage 2, the text is passed directly into the stage 2 using adaptive Huffman compression microservice. We implemented that completely from scratch using the FGK approach. We did not use libraries like gzip, zlib, or any built-in compression utilities, and characters that are appearing more frequently get shorter bit representations, which is less common in characters that get longer ones. Now, when a character appears for the first time, we send a special NYT, followed by the raw character bits. If the character has already seen before, we only send its current Huffman code. So every character, after every character, the tree updates itself by changing weights and swapping nodes to maintain the correct structure. Along with the compressed output, we also report the compressed size and latency, encoding efficiency, entropy, and original size. We also visualize how the Huffman tree changes over time. One important requirement in the case study was lossless decompression. So after decompression, we immediately run and compare the recovered text against the original OCR text. This verifies that no information was lost during compression and gives us 100% match score when everything works correctly. Overall, what makes our solution is strong, that is both stages are custom built. Together they form complete end-to-end pipeline, image in, extracted text out, compressed bitstream generated, and lossless recovery verified.